All right, so hello everyone, welcome to the reading group. Today I'm presenting a paper by Professor Rose, which is on temperature measurement and equilibrium dynamics of simulated annealing placements. It's kind of a mouthful. It's really actually not that complicated of a paper, but the math can be a little bit hard to digest. So I wanted to kind of provide this video as a way of being able to absorb the mathematics a little bit easier because it's actually not that complicated of an algorithm. I've implemented it in VTR and it did better than the default of VTR, so now it is the default in VTR. So it's important to know how this stuff works. So let's get right into it. Today is November 4th. Yes, it is. Okay. So first of all, simulated annealing. Now, the paper was actually written for ASIC placers, but this same principle applies to FPGA. Actually, completely the same. It's identical. So simulated annealing is actually what I'm showing here on the left, where we take a initial solution. That can be at random, but it needs to be a legal solution, and I perturb that solution. So we modify the placement solution. Let me just make sure this has some space. We're going to perform a modification on the placement solution. Now, notice how I say modification, not swap. It doesn't actually have to be a swap. A lot of people, when they think of simulated annealing, they think of swapping two clusters or something like that. You actually don't have to do that. It can be any modification you can imagine. It could be actually changing the contents of a cluster. It could be moving one primitive from one cluster to another. It's really any modification that you can do on the placement. We then, in the example of swapping the primitives, we can then evaluate the change in cost. So by doing this perturbation, how did the cost change? Did my wire length get better or worse? Did my timing get better or worse? Did congestion get better or worse? And if the cost is good, we accept it. Very happy. If the cost is bad, well, I don't want to just throw it away because I don't want to just go down the cost slope down to a global minimum, or sorry, local minimum. I want to do some kind of hill climbing. I want to get out of local minimums and find the global minimum. And how we do that is we accept with a probability, which is called the Boltzmann probability. I'll explain where this comes from in a moment, but this will tell us pick a random number. If you're less than such and such, accept. If you're larger, reject. And that's how that works. And we just repeat step one. Yep, reducing the temperature every so often. Now, where did the Boltzmann probability comes from? What's this concept of T? T is temperature. Where this comes from originally is something called annealing, which is an idea coming from metallurgy, where if I will have this beautiful crystalline pattern that gets formed when you are cooling down metal. And the idea is we act like we are these atoms of high energy in temperature, which is perturbing the solution. And as I cool the temperature, we form a more stable crystalline structure that's stronger. And that's kind of the key idea behind simulated annealing. We pick a temperature that's really high. When the temperature is really high, we're actually going to accept a ton of bad moves. You can kind of think of this as just kind of jumping around the cost landscape, not getting too bad. And then as my temperature lowers, I go deeper and deeper into a minimum. And hopefully, if I do enough of these swaps and I reduce the temperature slow enough, I can actually get to the global minimum. Not guaranteed, but I can get close. But now a question that I want to pose to everybody is, what do I use for the initial temperature? That's usually omitted from these discussions. Many people just say, pick a big one. But what is big? And what's the problem with picking a one that's too big? And what's the problem with picking one that's too small? That's what I'm really talking about in this talk. So in simulated annealing, temperature explores the amount of exploration. It tells you how much hill climbing you're willing to do. If you set it too low, you won't explore as much of the space, which may reduce the quality. That's not too bad though. At least you'll get decent quality, but it'll be not as good if you picked a high enough temperature. But is it bad to set the temperature too high? Well, if you set the temperature too high and your initial placement was random, not really. Set it as high as you want. There's still a drawback though. What's the biggest drawback that comes to your mind if I set the temperature way too high?
Runtime.
Runtime. That's the biggest issue. See, if I set the temperature to like a billion, trillion, quadrillion, it'll just take forever for that temperature to go down enough. But it's not bad if your initial placement is random. But I pose to you, what if your initial placement is already good? Then what's going to happen is your placement, which you spent a lot of time making a good placement, will get destroyed. And it basically becomes random. The higher you set the temperature, the more random it will become. And you basically just said, why even spend your time making that initial placement? So this is why it's really important to pick a good initial temperature if you are spending a lot of time creating an initial placement. So what's an example of that? Well, obviously, AP. With an AP flow, we actually spend most of our time not in annealing. We actually spend most of our time in other stages. For example, global placement and full legalization. We use these two stages to create a placement which is globally optimal. What we mean by that is that it has the overall shape of the circuit. Now, maybe a couple LUTs are switched side to side. They're not quite in their perfect spots, but the idea is that a LUT that wants to be on the left side of the chip is on the left side of the chip. A LUT that wants to be on the right side of the chip is on the right side of the chip. We spent maybe 2/3 of our runtime just creating that solution. Then we want to go into detailed placement. We do like a small fix-up, small details to further improve the quality. This is a great place for simulated annealing. This is what we want to use detailed placement for. But the problem is that if the temperature is too high, we're going to lose all of that global quality that we spent so long to create. And that's what we're trying to fix here. We want to try and say, what temperature should I choose for a flow like this, such that I can ensure the temperature isn't too high. Now, of course, if this was a static flow and you knew it was always going to be of a certain quality, you can just pick a temperature. In general, it won't change that much, given that your FPGA is the same and your placement flow is the same. But what if your placement flow is not always the same? What if you're tuning up your algorithm over time? You can't have a guarantee on the quality of this placement. So what you really want to do is look at the placement coming in and pick the temperature. So this brings us to a principle called equilibrium temperature. This is something you probably haven't heard of in Jason's course. So the equilibrium temperature is very simply just the temperature at which the average change in cost over a large number of modifications is zero. It's basically the expected change in cost for a given temperature. So basically, all it's really saying is this is the temperature that the overall quality of the placement will not change for a given iteration of simulated annealing if you pick this temperature, or it's the expected value. This is a good place to be, such that we can still hill climb, but we're not going to, the overall quality of the placement won't be destroyed. The basic idea being that we're not going to cause the initial placement to, we're not going to lose our global optimal quality. So that's going to be the goal for this paper. We want to not only study this equilibrium temperature, we want to see if we can find it. How do we deduce what it is? So this is where the paper turns to mathematics, and this is where things get very hard. And so I want to break it down very slowly. We're just trying to find the expected change in cost for a simulated annealing iteration. That means given a bunch of swaps for a given temperature. And I want to set that equal to zero so I can find which temperature does that. So we have this equation. Now, it looks really scary. It's actually not that bad. Let's ignore the integral for right now. For a given change in cost, let's say I did a swap and it gave me a delta C of +2. What is the probability that I saw that change in cost? That means if I did every single possible swap ever possible, ever being able to be seen, what's the probability of seeing a change in cost of 2? And then if the change in cost is 2, what's my probability of accepting it? See, 2, that means I've lost quality. It went up in cost. But because of that exponential term, I might accept it. So that's for a single delta C. All we're doing is just summing up over every possible delta C. So all we're saying is for every delta C possible, multiply it by the probability of seeing that delta C times the probability of accepting it. That's your expected change in cost. This is just the continuous form of this equation. You could also write this in its discrete form using summations, but this closed form is actually more convenient for the theory. But this probability of accept is actually can be broken up into two pieces because the probability of accepting a swap, if it's negative, if the delta cost is negative, we always accept it. So we actually break this into two pieces. The first one is for all the negative changing costs, and the right one is all the positive changing costs. So the negative ones, we just don't have a probability of accept. You just take the probability of seeing that changing cost times changing cost. The right side is the changing cost times the probability of seeing the changing cost multiplied by that Boltzmann probability. And our goal is to find where this is equal to zero. Is this clear? Yeah, so once it's spoken out, this equation is actually not that bad. And also, when you actually compute this, we don't actually compute the integral. You never do that. But this is a great way of thinking about it because you can actually discretize this using histograms to actually compute this properly. And without much loss in generality, you can actually get very close to a true solution by just binning everything, which I'm not even going to talk about because it's actually not that bad, but that's how you can think about this. So that's our expressions for the equilibrium temperature. How do we measure this? I want to, as you can see, this delta C is actually a term in the integral, and we know the temp, or we're trying to find the temperature, but what's this probability of delta C? It depends on the given placement. So let's get into it. What are some properties of the probability of seeing a change in cost? Well, the change in cost due to a move can be modeled as a Markov chain, where the change in cost due to the previous swap changes the change in cost for the next state. As I move from state to state, or from a placement to another placement, there's a probability that I'm going to move from one placement to another. That probability depends on a few things, which we'll talk about. The transition probability is the probability of going from one placement to another. And it's intrinsically a function of the move generator and the temperature. What do I mean by that? I mean that if I gave you an initial placement, if I told you that I could never do a swap that goes from the left side of the chip to the right side of the chip, that transition probability is zero. That's a function of your move generator. So the move generator decides what transition probabilities are possible for many things, and the temperature decides what bad moves will actually be accepted. And notice, actually, I didn't even mention this in the slide. I'm just going to fix that. It's also obviously a function of the placement because that changes the probabilities of it changes the probability of acceptances, or it changes the actual change in cost, which will then change the probability that they'll be accepted or not. And an assumption made by this work is actually a very basically said assumption, but it's quite integral to what they do. An equilibrium temperature exists for a given placement. It's weird you have to say that, but if you don't assume that this exists, it's not possible to ever find one. So we're just going to assume that one exists, and we'll talk about why you can be pretty sure one will exist, but I'm going to show you some diagrams to help. So far, do you guys understand what the probability of delta C is? It's really just your transition probabilities. So how does it change with temperature? What we see here is this is actually real data from a circuit. This is the probability, these are the transition probabilities for every single delta C. And what we see here is when the temperature is 5,000, notice how on the left side and right side, it's somewhat symmetrical. So the amount of the things that are reducing the cost and the amount of things that are increasing the cost are about the same. What does that tell you? Well, if the amount of things that the amount of good things and the amount of bad things are about the same, I'm at equilibrium. This is what we're searching for. And notice how as I increase my temperature, these distributions shift to the right, meaning that I'm going to be rejecting more things. Basically, the probability of seeing these are going to get higher and higher and higher, and we're not going to actually accept them. Yes. So the idea, oh yeah,
The positive delta C means quality improved.
positive delta C means the quality got worse. And so what this is trying to motivate is that the transition probabilities are dependent on the temperature. To be honest, I'm not sure if this has a typo in it or not, because this is a very strange graph. But they presented this in the paper, but the idea behind it is the same. As I increase temperature, I'm going to be shifting these probability distributions to the left, and as I decrease the temperature, it shifts to the right. I just can't remember if they did this dynamically or statically, which I'll talk about in a moment. So our goal is to find a temperature that kind of creates this kind of symmetric shape. We don't want things shifted to the right. We don't want things shifted to the left. And it should be pretty obvious. Well, yeah. So how do I actually measure that probability? Because I showed you some pretty graphs. How do you actually create a graph like that? So the key idea is that running simulated annealing at the wrong temperature, either too high or too low, will change the probabilities. For example, if I pick a temperature that's too low, I'm going to start accepting all of these moves. And what that's going to do is bring me down to a local minimum. That's going to change my equilibrium temperature. If I set it too high, it becomes basically random, and now my equilibrium temperature goes high. Basically, if you start doing simulated annealing at the wrong temperature, you're going to move towards that temperature as your equilibrium. It becomes the equilibrium temperature. So they propose two ways of doing this because that's actually a bad thing. We don't want that to happen. So they propose a dynamic method and a static method, with the dynamic method being not as good. The dynamic method's actually pretty straightforward. Pick a temperature and just go at it. Start performing all the swaps. Start doing all of your moves and do that for an entire iteration for a ton of swaps. Then after you've done that for a single temperature, you say, how has my change in cost changed? If it has changed, you're at the wrong temperature. So pick another one. And you just keep going. You go back to your initial placement, do it again. Go back to your initial placement, do it again. And iteratively, you're searching for the temperature where it actually stays the same. This is actually quite intuitive, but you can imagine this as being very computationally expensive. Every single time I change the temperature, I'm going to have to recompute all of those swaps. And you can't just do a few of them. You have to do a lot. Like they were saying in the paper for their circuits, 10 to the 4, 10 to the 5 swaps. So you do not want to be doing this dynamic method. However, this is the real equilibrium temperature. Like we know this is to be real because if you actually ran simulated annealing, that's what's going to happen. So that's definitely, it was good is that it's the correct answer. What's bad is that it's expensive. What would be nice is if we can have a static method. What if we perform virtual moves? We do a swap and no matter what, always reject it. Do a swap, no matter what, always reject it. Do that a million trillion times and get the distributions of the delta C's. Hey, look, I got my transition probabilities because now I know all the occurrences of the delta C's. And then I can use that so I can gather the statistics on the change in cost due to the moves, and then I can use that information to decide what temperature I should have used. Now, yeah, now you select a temperature that would have been in equilibrium for those moves a posteriori. Basically, using the data that you found, you figure out what temperature it should have been. Of course, this is actually relatively cheap. You only have to do those swaps once. You still have to do 10 to the 4, 10 to the 5 of them, but you only do them once. However, you may not actually be at the equilibrium. Or is it? So what they did in this paper is they actually did an experiment. They actually went through a bunch of circuits and said, okay, let's do the dynamic method and the static method, and let's see how different they are. And here's just an example of one of the distributions. This is the probability of delta C for both the dynamic method, which is the dotted line, and the static method, which is the straight line. Not very different in all honesty. In truth, it basically looks the same. They did note a common trend, though. The static method always overestimates the temperature, at least for the ones they've tested. They seem to find that it overestimates, which kind of makes sense. But the key idea is that if you pick a temperature using either the static or dynamic method, they end up being very similar. So that's kind of a really, really, really important idea from this paper. Empirically, we notice the static and dynamic methods resolve on similar equilibrium temperatures. And as such, we can use the cheaper static method to actually compute the probability of delta C. And we're going to do that in our final algorithm to actually get this to work. Is this clear, static versus dynamic, and how they're basically the same? Perfect. So, what is our algorithm for measuring temperature? I've just told you that the static method's a really good idea, and I've told you all these transition probabilities. How do I figure this out? Well, the first step is use the static method to perform a large number of virtual moves, recording the change in cost for each move. Note that the more virtual moves you do, the better the estimation. Now, they say in the paper 10 to the 4, 10 to the 5. We found in VTR we do about the number of blocks times the power of 1/3 or something like that. There's some equation you can do, but the idea is that you want to do a lot of these so that you can get a good estimation. And then what we do is we pick a random temperature. It can be any temperature you want. Generally, you want to pick a temperature that you think would be plausible for your circuit. Then what you're going to do is compute the expected change in cost using that equation that I showed you, those integrals. Now, as I said before, don't use the actual integrals. It's not that complicated to actually do this properly. The way the paper wrote this is in a general yet confusing way. And the more straightforward way of doing this is just pretend like you're the annealing engine. For every delta C you've seen, don't roll the dice, but get the expected value for each one. So for example, if the delta C is 2, then the expected change in cost is 2 times e to the power of -2 over whatever temperature you chose. And you go through that for every single one and you sum them together. That will be your expected change in cost. And here's the key, here's it. You do binary search. What you do is if the change in cost that I computed is negative, I picked a temperature that was too low, increase it. And if I pick the temperature that's too large, I need to decrease the temperature. And the key idea is that we can do binary search. If we need to, and the reason we can do binary search, I forgot to mention this very clearly, is because of this, how it shifts to the right or shifts to the left. The idea is that your transition the temperature changes how these distributions work, so that if the temperature goes up, we tend to always get a delta C that's too high. If the temperature goes down, it always becomes too low, or at least in theory. So that is our algorithm for measuring temperature. And I've actually implemented this in VTR. VTR's original algorithm was using the variance of the change in cost. So what they did was they did a bunch of trial swaps, and they just got the variance and delta costs and just used a proportionality constant for that. I changed it to this one, and we got basically the same quality, but 15% faster because we were at a better initial temperature. This was also much better for our analytical placement flow, which I was very happy about. So that's it. It was a very quick reading group this week. I just wanted to talk about this interesting algorithm. Now, let me see who's online. It's just Hong. Do people have any questions? Yeah.
Yeah, I think in the original equation to find the integral equation. So the left side, the probability of acceptance is 1, and on the positive side, it's temperature. That's the acceptance rate.
Yep.
So how does the later finding temperature equation encapsulate that part?
Oh, so you're talking about the algorithm that we proposed to actually measure this? So the idea, what's going to happen is you're going to get a list of a bunch of change in costs for a bunch of swaps that you've tried. Any change in cost, notice how there's a summation here. For each change in cost that you see, so let's say I see a -5. That was one swap that I performed, and I see a -5. Note, what's the probability that you see a -5? You saw it.
Yeah.
It happened. Now, later on, you're going to see another one. So in reality, what happened, it's 1 over the number of swaps that you've seen. However, and so that's kind of the idea here, but the point is we can actually ignore that division because let me slow down carefully because this is actually something that they don't talk about in this paper, but it's super important. When I've done a bunch of trial swaps and I see a change in cost like -5, the probability of that -5 is 1 over the number of swaps I performed. And if I had a positive one, it's also 1 over the number of swaps I performed. Notice that I have a division by n, the number of swaps on both sides. I can just multiply both of them by n and get rid of that term. So it always becomes 1 for you. And if you see -5 again, it actually sums naturally. So that's why the technique that I perform, where I go through each one and just sum them up, ends up being the exact same integral. It's actually the same probabilities. It's super interesting. So the idea is that you go through the list. If you are negative, just add to the running sum. If you're positive, multiply it by e to the negative whatever the delta C is over T, the temperature, and then add it to your running sum. And at the end, if that sum is zero, mazel tov, we're done. Does that make sense? Another fun thing about that equation is that it is guaranteed monotonic. So binary search is guaranteed to work. And it's not as fast as Newton's method. I tried Newton's method, it exploded in my face. I want to try and fix that someday, but binary search, this is not that long. Actually performing that binary search is not the long pole. The long pole is obviously doing all those virtual swaps. And actually doing this estimation is actually really fast. It's a really good question, Robert. I know you have a question? No? Hong, any questions?
Yeah, so for the dynamic methods, I'm a little bit confused. So how do they actually measure oh, so they do not measure the probability of a data cost, is that right? Or,
Mhm.
yeah, just a little bit confused how they measure the P delta C in the dynamic method.
That's a
Because
really good question. How they
yeah,
build this.
yeah, if they do not do the virtual moves, how do they measure the P delta C?
I
They,
also had the same question. I'm only speculating. They
mm,
weren't exactly clear, but they actually do accept the moves. The idea is they performed a ton of moves, and then they just they basically created a histogram where they
mm.
compute how many delta C, how many times did I see negative 400? Well, we saw that 40 times, and I did 4 billion swaps, so it's a probability of 1 over a million. The idea
And
is that they're going to perform a bunch of swaps, keep track of all the change in costs they've seen, and then they build up this distribution using a histogram. And they just set the bucket size small
oh,
so
okay,
that it makes sense.
I see. And it's all in the same temperature, right? So they,
Yes.
okay, yeah, that makes sense.
Yeah, it's
Mm.
actually kind of confusing, especially because the temperatures are changing. So if you're doing the
Yeah.
dynamic method and you're not at equilibrium, it's going to
Mm,
start to shift you towards equilibrium. And
mm,
that's what they kind of talk about in the paper. They say you don't use the dynamic method to really get this distribution. You use the dynamic method to detect, okay, am I at equilibrium or not? Oh, my actual delta C after performing all those swaps has become negative. Okay, this is definitely not the right temperature. But I believe when they generated this figure, they may have actually been at the temperature. Now, I'm not actually sure. It's hard to tell from this figure, but that or they just got lucky.
It could be they
y-
found equilibrium temperature with their dynamic method first, and then
Yeah.
at that temperature plotted.
Or the opposite. Either they found it with the dynamic method or they found it with the static method. There's actually a good table. I'll pull this table up because it's actually I didn't put it in my slide because I didn't feel like this paper didn't have that much data that I thought was like, you must know this data. But they did have some good data on, I don't know why this is taking so long. There we go. So they had some good data on the difference between the dynamic method and the static method. Let me go to that. It's on the last page. I always love these papers because you get like this hyper compressed version of Professor Rose, and it's always the same picture too. So it's just kind of it's really fun to find, just because this was photocopied. But if you look at this table, you can actually see the difference between they call it binary search and the delta method. The delta method is basically the dynamic method, and this is the static method. You can see the difference in the temperature. As you can see, it's practically always higher to use the static method than the dynamic method. How I interpret this, though, is that this is the true equilibrium temperature. If you actually ran simulated annealing at a temperature of 374, you would expect to find a delta C of 0. Does that answer your question, Han?
yeah, yeah, exactly. Yeah, thank you so much.
Wonderful. Any other questions? No? All right, I'm going to stop the recording. Thank you all so much.